Then the extended day. I was going to have a class on the 24th anyway, but it didn't have to be a big deal because it was going to be reviewing any questions you had for the final. So either way is fine with me. It seems like we're going to meet on that day anyway, July 24th. Is that agreed? There's people who want to be gone can be gone, right? If they're gone already. Yeah. So we're going to meet on July 24th, but you want to make sure the course is complete enough before that time that you don't have to learn new stuff on July 24th for your exam being submitted on July 26th. That is correct. You would not have to. So I'll adjust in such a way that we can meet on July 24th. And then officially in the final exam date, we'd also have to have a meeting, okay, on July 26th to make it kosher. But I believe that usually if it's a take-home exam, nobody meets anyway. Okay. So that's a possibility. Okay, so that leaves us in somewhat of limbo. At least one person wants to get done with the class earlier because they're going out of town or starting a new job or something, and another person wants to be out of town on that day. Yes?
Well, it doesn't really matter to me just as long as I know that I can have like a final grade either on or
okay.
Or some idea.
Okay. Yeah, I understand that. Okay. Well, yeah, I can certainly make an estimate of your final grade. Okay. So, does anybody else have any comments about it or questions about it? How many other people were planning on not being here on the 3rd? Just one. Okay. How many people would rather not be here on the 3rd?
From the class, because my class doesn't have anything.
Woohoo! You wouldn't have to come to class. It's a not matter. Nobody has any feelings one way or the other? Okay.
We're math people. We don't have lives outside of this.
Okay, well, why don't we just have the meeting then? Let's go ahead and have it on the 3rd because it's better to have the extra meeting, I think, and just get it finished. You'll have to read it up on the thing. Are you okay with that, Nicholas? Okay.
But the midterm will still be due on the 5th?
Yes, midterm will still be due on the 5th. So you can ask questions on the 3rd. If you're not here, you'll have to email me questions, okay? Or read them, the other people's questions on the download. Is anybody having any success yet downloading the lectures? Anybody tried? Okay. Talk to these people. I figured you would have by now. But, okay. There was a question about how would you actually compute this standard error that I computed here. So the standard error of beta 1 hat in the delivery time data is actually equal to sigma hat times the square root of what I'm calling capital C11, which is the square root of 10.62 was that 233 divided by 22. That's the 10.62 for sigma hat squared. All right. This was the 233 point something divided by 22 was sigma hat squared. Okay. So it's the 10.62, and then there's a square root of the what I'm calling the this is the second diagonal entry of the 3 by 3 capital C matrix, which was 0.002747. So this comes out to be 0.167. All right, standard error of beta 1 hat.
And the C is just X transpose X inverse?
Yes. Capital C equals C00, C11, C22, and then other entries, which are also coming in when we actually make the other estimators, right? C01, C02, C12, etc., etc. And it's symmetric, so I might as well leave those other ones out. Okay, equals X prime X inverse. So there's no sigma in the capital C matrix. It depends only on the X values. All right, corresponding with previous calculations. All right. All right. F test for significance of regression. Do I need to go through this? I'm not sure. What I do need to do is come up. Well, last time we had, for simple linear regression, we had SS. We actually calculated the expectation of SSR on one of those handout sheets I had. I don't know if I ever handed it up in class, but it was on the website. It showed, and I did show in class, I believe, how to calculate the expected value of the regression sum of squares. Calculate ESSR as K sigma squared plus some positive term, which is denoted this way in the text, BR prime XC prime XC. Beta R. Okay? Okay, well, that needs an explanation. What is beta R and what is XC? Okay? Here's what it is. I'll explain. Where beta R is just a K by 1 vector, which is beta 1 through beta K. Capital R stands for reduced in this case. Well, I don't know if it does. I don't know what it stands for. But anyway, it's take off the beta 0. Maybe for regression, but anyway, just the slope coefficients here. Okay, and x sub c. What is x sub c? X sub c is the following matrix. It is x11 minus x1 bar. You correct each column by the mean of the regressor in that column. xn1 minus x1 bar. So you take you don't involve the 1. So instead of, it's just the x variables, and you correct each column of x's by the corresponding mean of that column. So corrected, if you want, x12 minus x2 bar, x22 minus x2 bar. So you think about the x's being in a column in your spreadsheet, right? You have the number of cases. Subtract the number of cases, subtract the mean number of cases in your data set. Then you have the number of feet traveled in the delivery time data. Subtract the mean number of feet. And so on. And then you have the last regressor, x1k minus xk bar, down to xnk minus xk bar. So that's actually what x sub c is. And if I take xc prime xc, what am I getting? I'm just getting what do you get? If I take, for example, this if I take xc prime xc, when you do that, is various inner products of the columns of this matrix. Because it's taking this columns and making them rows, and then taking inner product. So what it is when I take xc prime xc is I'm taking this column into this column into itself, and so on. All the columns into each other. Okay, for the ij element. Ith column into the jth column. All right. So what would that be? If I take this column into itself, I'm getting the sum of the xi1 minus x1 bar squared. So this would come like this. Summation. So you would just get the variability of the first column of x's. You would get the variability of the second column of x's on the second diagonal element. And then you would get the covariabilities on the off diagonal element. So you would get summation xi1 minus x1 bar times xi2 minus x2 bar. I goes from 1 to n. It was just one summation index. I goes from 1 to n. I goes from 1 to n. Okay? Covariabilities. Okay? If I properly normalize them, I get variances and sample variances and sample covariances. I divide by n minus 1 to get sample variance of the x's. Divide by n minus 1 to get the sample covariance between x1 and x2. So that's what that matrix is. And actually this should fit, let's see, because what I said was and then let's see, if I actually do this times, what did it come out? It came beta 1, in the simple linear regression case, it came beta 1 squared times SXX. For the k equals 1, this becomes equal to sigma squared plus beta 1 squared times SXX. It comes out that simple. Okay? In the case of simple linear regression. All right? Because what that is, this is SXX, right? SXX. You just get a 1 by 1 matrix for this x sub c prime x sub c. This is a k by k matrix only. This is a k by 1 vector. Something like that. So you get the 1 by 1 times beta 1 squared. And that's exactly what we had before. In other words, that the ESSR, MSR, therefore, because that's the same thing as SSR in the case k equals to 1, was an estimate of sigma squared, which is unbiased with sigma squared if beta 1 is equal to 0. So under the null hypothesis, this gave an unbiased estimate in simple linear regression for sigma squared. So what I really had in my F statistic was a ratio of estimators for sigma squared. Okay, both of them unbiased under the null hypothesis. But when the null hypothesis failed, the denominator, sigma hat squared, was always unbiased for sigma squared. The numerator had a positive bias for sigma squared. Remember that? F is equal to MSR over sigma hat squared. Okay, that's your F naught, and you have the null hypothesis that beta 1 is equal to 0 for. This is simple linear regression. Okay, so what happens is you get the ratio of two unbiased estimators of sigma squared under the null hypothesis, because under the null hypothesis I got a sigma squared here. In the denominator, roughly, I have a sigma squared. Okay, but if the null hypothesis fails, if beta 1 is unequal to 0, you get a positive bias in this term. SXX is a positive number. Beta 1 squared is a positive number. All right, and the bigger the beta 1, the bigger the bias, right? So what you would do is that if this ratio came out bigger than something middling like 1, sigma squared over sigma squared is 1, then you would reject the null hypothesis. It made sense because you always had a positive bias in the numerator and no bias in the denominator. That's the whole basis of the F test. So what we're getting here is that this is also a positive bias. Of course, I have to normalize by k to get MSR, because k is bigger than 1. So now MSR is not the same thing as SSR. It's SSR divided by k. All right? Get your variance estimator for the numerator. MSR. Reject H naught if F naught is large because of this positive bias. All right? See, is it making sense? In other words, just going, I'm not writing it down. Numerator has positive bias. For sigma squared if H naught fails, while denominator is always unbiased. While denominator remains unbiased for sigma squared, independent of beta 1. Okay?
So this is in reference to the simultaneous confidence intervals on regression coefficients?
No, I'm not getting there yet.
Okay.
I'm not going to get there today.
Okay.
In fact, I didn't assign any homework on simultaneous confidence intervals. We may not discuss that because of the short time we have this summer.
So
I'd love to. Phase method, other methods, Bonferrone's method.
when will we, should we always use this as opposed to the t-test?
No. This is equivalent to the t-test for beta 1 equal to 0. This is equivalent in simple linear regression. For multiple regression, it tells you basically whether the whole model gives you anything at all. Okay, it doesn't tell you about individual regression coefficients.
All right.
Okay, this tells you, this is equivalent to the t-test for beta 1 equal to 0, okay, in simple linear regression. This f-test is equivalent. You get exactly the same p-value. Look at it on your simple linear regression cases, all right? For multiple regression, and I was going to get into that a little bit more in this hour, they're not equivalent now. All right, you have the t-test for the individual coefficients, and you have the overall regression. Does the model do anything at all? That's what I'm saying. The F statistic should always be significant in multiple regression. All right, if you've thrown everything you have at the problem and it still doesn't give, then either the sample size was too small, or you just didn't throw the right stuff. Okay, or you got the wrong. You just have the wrong model. You don't have the right polynomial model or something. Okay. I think there was one example in your simple linear regression, though, where f naught was not significant, right? That last problem you had to do on last assignment. That was kind of interesting. Problem 2.13, the model was not significant with just simple linear regression. Somehow ozone was not, the number of days that the ozone exceedance had occurred did not relate to the temperature index or something.
Days over a certain temperature.
Yeah. I'm not sure how that worked, but anyway, that just was a great guess, but it didn't work out. Okay. All right, for that particular scientific inquiry. Okay, so this, let's say how at least that this is positive. Okay, what is this now? This is actually the square norm of a vector, is it not? Because it is xc beta r, which doesn't make sense as a product, and then times the transpose of that product. Okay, so this is the norm square. All right, this expression means you take off the beta 0.
Oh,
okay. Okay, so br times xc times br norm square is br prime xc br. All right. So indeed, this is a non-negative quantity. Okay. So actually, you do have a positive bias then again in this case, in the general case. And so you take MSR equals SSR divided by K, then EMSR. Okay, that's the definition of the mean square for regression. EMSR, therefore, is equal to sigma squared plus 1 over K times this beta R prime XC beta R. Okay, so this is unbiased for sigma squared under H naught. All of the slope coefficients are equal to 0, which is the hypothesis that you have a trivial relationship only. Okay, trivial relationship only. Constant for the mean of y. This means that EY equals beta 0. Okay? Right? You don't want EY equals beta 0 usually, okay, unless all your regressors are crummy. So, unbiased under this model and positive bias otherwise. Let's see. I guess we'd have to argue that since the rank of X was full, this also has a full rank, this matrix, okay, and so it would be invertible. So this matrix, so this product XC times BR is non-zero vector, if and only if beta is a non-zero vector, okay. So this is invertible. Invertible. since x n by p has dimension p. What have I done? I've taken a constant multiple of the one vector and subtracted it from each of the k remaining columns. All right. So that has left the x sub c matrix with rank k. All right. Has not lowered. It has left it as a full rank k. So x sub c prime, x sub c would still be invertible, and so this will actually be non-zero precise. This bias will be non-zero precisely if h naught fails under these assumptions. I think I better not go through the derivation of this ESSR. All right, that's just going to take us too long. But it's there on page 3 of these notes. Okay, so that's the same. That's the. I mean, it's kind of nice to go through see how our calculation here was generalized. You know, it is kind of a nice calculation, but it's something that we've done before. So I'm going to skip it for now. Okay. What I want to discuss is the extra sum of squares method and the general linear hypothesis. Gosh, I don't know how far I'll be able to go with this. Let's see if I can finish it, though. I've only got 8 pages of calculations to go through. All right, so I've explained the calculation. I haven't done all the calculations, but I've explained the meaning of these things so far. Okay, so now
we talk about the extra sum of squares method.
Yes. This is going to be used throughout the remainder of the course, discussing, you know, whether one model is better than another and so on, and getting F statistics. Okay. So generally, what the idea is that what you're going to do is you're going to have a certain number of regressors in the model, and then you're going to add another one and see what the contribution of that regressor is by adding it in. All right. Or by taking it out equivalently. What happens is you add it in and you take it out. You change the sum of squares accounted for by the model with respect to that added in or taking out variable. Okay? So what do I mean? I mean you have a certain number of columns of the design matrix X. That's the regressors you have. And you add one in, you get a bigger column space, right? If you add a new regressor in, you get a bigger column space. Well, that means the distance to Y will be reduced, right? You have the projection on that column space, and the distance between the projection and Y will therefore be reduced. If you get a bigger space, hey, the Y vector is where it was. I just made, you know, a bigger hill, you know, to get up to the sun. Okay, I'm closer to the sun now. Okay? The column space is bigger. So, all right. So the distance. So that's the change in the sum of squares is called the extra sum of squares. Okay. So it's the amount that the residual sum of squares changes by, which is equivalent to the amount that the regression sum of squares changes by. Okay. Now the only fine ointment is that we're not only going to consider we're always going to be in the column space of X somehow, but we're going to allow lines or planes that lie in the column space of X that don't pass through the origin. Okay. So we're going to consider linear varieties, all right, to project onto, things like that. Okay, so that was under the general linear hypothesis. Okay, but here's what I'm going to do. Get a new pen first. Okay. Extra sum of squares method. So it's pretty geometrical, is the point that I'm making. What you're going to do is you're going to partition your vector of parameters beta 1 to beta 2. So one of these is going to be p minus r by 1, and then you're going to r by 1. So and I'm going to consider h naught beta 2 r by 1 equal to 0, 0, 0, 0. So I'm going to basically be taking regressors out by this method. I'm going to say, let's look at the reduced model where I take the last r regressors out and set them all equal to 0. Okay? So presumably beta 1 has the intercept in it. But this is totally general. This may be for intercept or no intercept model. Okay? This is your p by 1 vector. Okay, that's the way you're going to partition the regressors. Right, the full model, which is going to designate by the abbreviation FM, is going to be y equals x beta plus epsilon equals x1 beta 1 plus x2 beta 2, where now x1 and x2 are the correspondingly partitioned pieces of the X matrix. X is equal to x1 and x2. The first P minus R columns, and then the last R columns of X. So, you're going to partition the X matrix into its first few columns and its last R columns. All right? The reduced model, which is when you take out these last R regressors, is simply, therefore, y equals x1 beta 1 plus error. Okay? Okay, so what I'm going to do geometrically is I'm going to have my big model for means, this is the full model, is a plane to the origin. Okay? And my reduced model is going to be just simply a line to the origin. So I'm going to still work with subspaces at this point. So I'm going to have two subspaces. This is a set of all x beta in RP. This is the set of all x1 beta 1 in the only has P minus R coefficients. Okay, that's the line, right? And though first I can project, now take your y vector. First I can project onto the plane, okay, and then I can project from the plane onto the line, okay. That'd be a double projection, okay, or I could actually just project directly onto the line, okay. That would be, and so here I have what h1y, I have hy, and I have y, where h is the projection matrix corresponding to x, h1 would be the projection matrix corresponding to x1, so h would be x prime x inverse x prime, and h1 would simply be a small, this is a, well, they're both n by n matrices, okay? They're both n by n matrices. The one's a projection onto the full model, and one's a projection onto the reduced model. Okay? That's simple enough. And so I get my two possible predictions. All right. So to get the prediction with fewer regressors, I don't just set I don't take the full model predictions and just set all the other regressors to 0. It doesn't come out the same. It doesn't come out right. Is everybody following what I'm saying? If I had y hat equals beta 0 hat plus beta 1 hat x1 plus and so on plus beta k hat xk, and my reduced model was to throw away the kth regressor, all right, the prediction would not just be to take the full model coefficients and throw the last term off. The prediction for the reduced model would not be to just throw the last term off. That is not correct. Only in orthogonal models would that work. All right, if that's if the columns of X are orthogonal, then you can do that. Okay? we'll see that and that's actually useful so you don't have to recalculate the models over and over again if you're studying certain polynomial models. So in section 7.5, if we ever get there, all right, this will be one of the applications of actually taking design matrices where the columns of X are perpendicular. You don't have to do a lot of recalculation to see how models fit. You just throw some of the terms off, okay, from the original calculation. You don't have to recalculate. With modern computing devices, that doesn't seem so necessary anymore. But there's still problems if the columns are actually somehow almost linearly dependent, and that still causes trouble. Okay. All right. So beware of that. So I'd have to recalculate, this H1 matrix if I wanted to throw off the last regressor. Everybody following? Okay. Now, we define sum of squares according to how many regressors I have. I lost my center line here. Where is it? This looks pretty good. Okay. Okay. SS sub R of beta. He's got a bold-faced beta in there. This is the not the usual SSR because it's not adjusted for the mean in this notation. Not adjusted for the mean. Okay? This is defined to be simply beta hat prime x prime y. Okay? Which was the square length of the projection. Okay? Square length of y hat, if you want. Alright, but I'll just call it hy because there's too many y hats. Okay? And then SSR, if I took the reduced model, then that's the uncorrected model sum of squares, which is beta 1 hat. Well, I should write it this way. I'll put it h1y norm squared. I'd have to recalculate the beta 1 hat, like I said. Okay? And then put x1 prime y, so the beta 1 hat. So that's why I'm not writing beta 1 hat prime. Maybe I did in the notes, but beta 1 hat prime has to be calculated. Where beta 1 hat prime, beta 1 hat is equal to x1 prime x1 inverse x1 prime y. Okay? So I can't just get the beta 1 hat from the beta hat by throwing away the last r terms. Right? So be careful what beta 1 hat is in that notation. And then we simply put SSR, the extra sum of squares, is just the geometry. SSR beta, he's just got this notation, beta 2 given beta 1, okay, is just the difference. SSR full model minus SSR reduced model. Okay, which actually is, if I do now correct them for the means, this simply is SSR full model minus SSR reduced model. The only difference in this equation is that these were the unadjusted SSRs, but since the adjustment is the same for both of them, namely ny bar squared, it comes out to be the same as this. So let's check this out. So let's check out let's take the rocket propellant data, page 90. I hope he's got the two regressors here. I think he does. Let's see what it actually is talking about. This is very simple.
page was on again?
90. Okay. He's got SSR full model equals 50.81. I'm just going to truncate the digits so that everything comes out nice up to 2 digits. Okay? I'm not going to round. 50.81. Okay. What's the reduced model? Suppose I take out the second regressor. Now I could take out either the first regressor or the second regressor, but suppose I take out the second regressor. Okay, how would I get the SSR for the reduced model? I would just go back to the rocket propellant data that was in chapter 2. Okay? And look at this analysis of variance table. I'm looking at 2 different analysis of variance tables. One for 2 regressors, one for 1 regressor. Right? So leave only the first regressor in. In rocket propellant data, let's see, what was the situation? They had example 3. Do I have the right? Oh, maybe this is not the rocket propellant data. Example 3.3. Maybe I have the wrong one. I might have called the rocket propellant data. It should have been delivery time data. Sorry. I think he's only on delivery time data here. Please.
Yeah, delivery time data.
Sorry. I think we saw this one already. What's the reduced model? This is our full model. Is this? What's the reduced model sum of squares? Suppose I only have the number of cases. I can get that from chapter 2 because that's the last example in chapter 2. Suppose I only keep the number of cases in the model. Then on page 58, you get SSR reduced model, which is corrected for the mean. In this case, the model sum of the squares is 5382.41. Okay? Near the top of page 58. Delivery time data. So what I'm doing is I'm looking at 2 analysis of variance tables. One where I throw all the regressors in. The next one where I leave one of them out. Okay? Now you can see you would get presumably a different extra sum of squares depending on which one I left out. Right? The difference is the extra sum of squares. Okay? Which is this right here. Right? This is the difference between the 2 models. This is the extra sum of squares. The square length of that side. Okay? By the Pythagorean relationship. SSR reduced model plus something equals SSR full model. Okay? So this comes out to be, what is this? So this SSR beta 2 given beta 1, therefore, after beta 1. Fitting beta 2 after beta 1, okay, is how you could read this. The extra sum of squares accounted for by fitting beta 2 after beta 1. So you can either talk about adding it in or subtracting it out. By fitting beta 2 after beta 1 is equal to 5550.81 minus the 5382.41 is equal to
168.4.
Oh, very good. 168.4. That I do remember that number. Now, I could also get this as just a difference of the residual sum of squares. Right? This is equal to, no, this is the SS res. Let's see, the SS res of the reduced model is the bigger one. You're further away from the sun, okay? Because you're in the small model, okay? SS res reduced model minus SS res full model. So again, I could just look at the two analysis of variance tables and read that out. The reduced model, this came out to be the 402.13, and then the other one was the 233. I remember that number, point something. 70 what?
2.
I'll put 73. Okay. Anyway, something like that. Maybe it was 0.14. 0.1270. Anyway, to make it come out to 168.4 again. All right. So that's the extra sum of squares method. By the Pythagorean theorem, it comes out you subtracted either way. Now, and so what does that give you? All right. Well, then it turns out that that thing, E of SSR, beta 2 given beta 1. Again, there's a long calculation which I've shown in the notes, but I don't have possibly time to show here. Is equal to R sigma squared plus something looks like this: beta 2 prime x2 prime. I went through it myself all day yesterday because I wanted to understand it completely. But now that I've understood it, I'm happy just to display the answers. Okay. Because it would just take us too long. It's from the appendices. But I take you through it so that you could follow it in these notes if you really wanted to. Okay? Times x2 beta 2. There's a formula, again, a nasty looking formula for what this extra sum of squares expectation is.
Where R is which R?
The number of regressions you've tossed off under the null hypothesis. This little r. This little r is so it's 1 in our case because I just took one regressor off. So the number of regressors you dump, okay, to get to the reduced model. Officially, if there was some linear dependence, it would be the dimension of the column space of x2. Okay? Okay? So, let's see. This comes out to be this. This is a non-negative matrix. Okay, it turns out. Because what this is just the what the square length. See if I took this vector. Let's see, what would this be? Well, yeah. I mean, if I take this is a non-negative definite matrix. Okay, if I took y prime I minus x1 prime x1 inverse x1 prime. Okay, and then y. Okay, this is going to be non-negative for all y. All right, because it'll be because indeed this is just this is simply what we calculated as the residual sum of squares. Okay, so the residual sum of squares for projection onto the reduced model. Okay, so that's certainly a non-negative. So this is a non-negative matrix here, and I've got, I have something of exactly of that form: y prime times this matrix times another y. So this is a non-negative quantity. Okay. So this is certainly non-negative. Okay. In fact, presumably this is in this matrix here is invertible and so on and so forth. So. On all the good assumptions. So this is going to have a positive bias for R sigma squared under, let's see, except under the null hypothesis beta 2 equal to 0. So I'm exactly going to be able to capture the hypothesis beta 2 equal to 0 by using this extra sum of squares method. So, ESSR, so beta 2 given beta 1 divided by R, okay, is unbiased. Excuse me, SSR over this is unbiased. I don't even give this a name, I just call it that. But actually, no, I call it this, SSH divided by R. We do give it a name, SSH. And it's not that other software we were talking about before. Okay, it's SSH. Okay, for H the hypothesis. Sorry, SSH divided by R equals this is unbiased for sigma squared under H naught. Beta 2 is equal to the 0 vector 0, 0, 0 R by 1. So you're setting R regression coefficients to 0. The last ones, presumably, that you want to deal with. However, you're ordering the regressors in order to do what you want to do. Setting the last R regressor is equal to 0, and it's unbiased. This quantity is unbiased for this. So I have yet another name for this extra sum of squares. I call it SSH.
That would again be an F test?
Yes. So now again, because of the independence assumption we've already have, sigma hat squared is going to be independent of this. Because remember, because you have the orthogonality. All this SSH is like a sum of squares coming in the model for the full model. Okay? There's a vector in the full model, and you're looking at the square length of it. It's orthogonal to anything which is perpendicular to the full model. Okay? So you actually have independence with sigma hat squared by the normality assumption. That's how I think about it. Okay? If you got orthogonal vectors, they're always orthogonal. Okay? Then you have independence. Okay? So now, so therefore you have F naught equals SSH divided by R over sigma hat squared is distributed as F R comma n minus P under H naught, and is is non-central F. Okay, if H naught fails. Okay. We haven't talked about non-central F, but basically the numerator is biased in exactly the same way we've shown here, with a positive bias.
SSH is just that gigantic thing which has circled there divided by R?
No. The gigantic thing, no. It's this difference of the residual sum of squares. This is SSH. Okay? This is the bias term. This divided by sigma squared is the non-centrality parameter. Okay? This equals sigma squared times lambda, where lambda equals the non-centrality parameter. If you read about non-centrality parameters, that's what they're talking about. Okay? What you have is that you have F tests. You have F statistics, you have non-central Fs. A non-central F is exactly one of these things which is, let's see, what is an F? An F is a ratio of normalized chi-squares. Right? An F R n minus P would be a chi-square R divided by R over a chi-square n minus P divided by n minus P. Okay, that's what an F variable is. Okay? Distributionally, where these are independent. So what you have two variance estimators, and of course I can throw my sigma squared in here for free. Okay? My two variance estimators are of this form. Under the null hypothesis, the numerator is of this form. Under just the plain old normality assumption, the denominator is of this form. So is independent of whether H naught holds or not. Okay, my sigma hat squared. These are independent under normality assumption. Okay, now what the non-central F is, if the null hypothesis fails, you don't actually get a chi-square, you get a chi-square prime. Okay, so non-central F is with a chi-square prime in the numerator, where chi-square prime means you're not taking the sum of squares of centered standard normals. You're taking the sum of squares of non-centered normals. In other words, and the sum of the squares of the means is actually the non-centrality parameter. Okay? So if I take summation zi plus mu I squared, I goes from 1 to n, then this is a chi-square prime, okay, of, well, let's put it nu here, nu, where these are standard normal, and mu is just constant, where this is with non-centrality parameter, just the sum of the squares of the mu's. So it doesn't matter what the mu's are, actually this will have the same distribution as long as the sum of the mu I squared is the same. Okay? So it actually depends, the distribution of this random variable only depends on lambda. Okay, that's the point there. Okay? Which is, again, a little too far afield for us in this course. All right. I hope I have this right. To the math gods. Anyway, it's my best effort because I didn't review this non-centrality stuff for today. Okay, so we should check up on that again. Double check Morrow. But I do know it's a non-central chi-square over this chi-square, and the non-central chi-square has a simple definition. All right. The distribution only depends on the non-centrality parameter. Okay. So, exactly that way. And so the non-central f is going to be larger than the f, okay, than the central f, where you have centered normals in there. Okay. So you've got this bias coming in, and that's what gives you your test. So you have f-test. So now what happened? What is... Now the point is that somehow the individual t-tests for the individual are equivalent to these f-tests with little r equals to 1. So this is the theorem that if I take SSR, that if I take SSH, well, let's put it this way. Let's put H naught beta j equal to 0. Okay? Then SSH is equal to SS R beta j after all the other ones, beta 0, beta 1 up to beta j minus 1, beta, then skip beta j, go to beta j plus 1, and beta k. So you're fitting the jth regressor after all the other ones have been fit. Okay? So either you're leaving it out first and then adding it in, or you're taking it out. Okay? And then the extra sum of squares is coming here. Okay? The difference between the SSC. So this is SS res reduced model minus SS res full model. So what you do is you fit the model without the regressor, the jth regressor. That's the reduced model. You get a certain residual sum of squares. Then you throw the jth regressor in additionally to the other ones that you already had, and you get it. And then you do the analysis of variance again, and you get a smaller residual sum of squares. Take the difference, and that's your SSH. Now the theorem is that SSH divided by 1 over your sigma hat squared, which is your F statistic, okay, is the square of the T statistic, where T naught equals to T equals your beta j hat minus 0 over the square root of Cjj times sigma hat. Okay? Was your T statistic for testing the hypothesis that beta j equal to 0. Okay, so all these T statistics you get for the individual regression coefficients can be interpreted as adding that particular regression coefficient as the last coefficient, as a single last coefficient to make the full model. Or is taking that one out. So you've actually got a bunch of different model analyses already. So it's not like adding it in after only the first couple. There's a couple ways that might be interpreted that you might have thought of if you didn't have this theorem. Okay, you might have dreamed up some other ways that you could interpret the T statistics for the individual coefficients, right? You're going to thought, well, the model is being built one after the other. Okay? But that's not how it is. It's like you take the full model, all of them in, and take one of them out, and that would be whether that regressor is significant in that situation. Okay? There are different ways to build a model. That is, you could actually do forward regression, and then you get different t-statistics. Okay? Where you're actually just adding them in one at a time. That's different, because then you have a whole bunch of different full models. You have the chronologically developed full models. Right? Okay. So that was the theorem. What's the general linear hypothesis? I did want to do one last thing and give an example. This is going to be a little tricky, but I think I can give the gist of it. Okay. What you also have is a general linear hypothesis. Page 6 of these notes shows a picture.
I think the notes should be pop-up notes.
Which means?
You know, when like pop-up books, you hold them and things fold up so you could actually like see all these geometries.
That'd be cool. I've seen books like that where they actually have pop-up books. What was that? It was an art book or something? Oh, I know, it was an architecture book or something like that. Where they actually, you know, the actual architectural design or whatever like pops up out of the book. It's pretty cool. Anyway. So yeah, the idea has been used. Page 6 of these notes. There's a general linear hypothesis. Suppose I can do the following. Think in terms of constrained minimization. You're trying to find remember when we did the least squares solution, we took partial derivatives? So we actually took the distance from the point to the column space of x and took that as a function of the betas and said, okay, that's a function I need to minimize in order to find the least squares estimate in order to solve this projection problem. I'll use partial derivatives to solve the projection problem. Hang it all with linear algebra. I don't need linear algebra. I just take derivatives, right? I don't need a projection matrix. Okay. Okay. So what happens now if I do that? Now your bright fellow student said, well, what happens now if I add a constraint to that problem? Then it's Calc 3. Okay, so here's your x beta. And now I'm going to take a constraint of the form t beta equals to c. Now you're going to hate me, but this is an r by p matrix, and this is your p by 1, and this c is an r by 1 matrix of constants. Alright, so this is an r by matrix, and this is a matrix. This is a constants. So I'm going to have some linear constraints like beta 1 minus beta 2 equal to 0. I mean, in some cases it might be reasonable that you would say, well, the actual slope parameter should be the same in some weird context. I'm going to have an example context where I study a certain type of data, and the data will be such that you have one kind of simple linear relationship if x is less than or equal to a cutoff like x equals to 10. But when x is bigger than 10, there's a different linear relationship. So what if I had a situation like this? I've got one straight line fit to the data, but after a certain point, maybe either with or without continuity, I had a different straight line fit. Okay?
That's just evil.
That's just evil. Okay, but that's the kind of data where there's a bend in it. Well, that's reasonable, right? Like a threshold phenomenon with a different slope. Okay? Sales are going up at a certain rate, and then after a certain point where there's been a lot of things sold, hey, they're not as expensive. They're not, as expensive anymore, right? So that would be an example of a simple case where you had that could be modeled in terms of linear modeling. Okay. So that can be handled by the general linear model, which is what this x beta thing is. But this is the general linear hypothesis, which would be, linear constraints on the betas. That's all. You're only allowing linear constraints on the betas. But you can do that, and you can talk about, so that would give you, if you apply this hypothesis, H naught T beta equal to C, okay, you can think of it as a hypothesis. It's just more general than beta 1 equal, or beta 2 equal to 0, right? Beta 2 equal to 0 certainly can be put into this context, right? But put it to corresponding T matrix, just a bunch of zeros. So beta 2 equal to 0 with P equal to 3 would be 0, 0, T would be 0, 0, 1, and C would be equal just to the 0, 1 by 1. Okay? Right? That would be a simple case for very trivial T. I don't even need to talk about T, but here if I want to make this more general hypothesis, I would. It just turns out to constrain minimization. If I want now to, I'll get some kind of linear variety as a subset of x beta, set of x beta such that T beta is equal to C. Okay? Would be this thing now. It doesn't have to pass through the origin, right? Anymore. So I can find, the distance from the y to this linear variety, right? This other plane that's not passing through the origin. Certainly, if you think about it in Calc 3, I can take a point, distance from a point to a plane, right? The plane doesn't have to pass through the origin. Okay, so I can do that problem. Okay, and then you still have the question of whether you have the full model, then you have the reduced model, then there's still an extra sum of squares here. So this is now the extra sum of squares. And they have a very fancy formula for it. Okay? Namely, it is SSH is equal to T beta hat minus C. Now I put in the beta hat in place of beta. T beta hat minus C prime T x prime x inverse T prime and then T beta hat minus C. Okay. The nasty looking formula. Okay. Now, is there another inverse here? I can't remember here. Yeah, there's probably another inverse here. No, I can't remember. Now, can't remember. No. Can't remember dang formula. Yes, there's another inverse sign. Wait a second. No, there's not an inverse sign there. Where is it? Yeah, okay, there's another inverse sign here. Okay. Okay, there's a nice formula. Now that you can actually get by the method of Lagrange multipliers, and I do it in the notes.
You can get that formula that way?
You can get the formula as follows. There's problem 328. If you get into the Lagrange multipliers, problem 328 in this text, there's actually a couple of decent problems in this text. It's kind of hard. There's a small typo in problem. But it gives you that for the constrained minimization, beta tilde equals beta hat plus x prime x inverse T prime and then a T x prime x inverse T prime. There's a typo here. There's this one prime is missing. Inversed C minus T beta hat. Instead of putting T beta hat minus C with the minus sign here, he's got a plus sign and then a C minus T beta hat here in his formula. This is the value of beta tilde that actually does the constraint minimization. Okay? So in other words, this point is x beta tilde. Okay? And this point is x beta hat. Okay? This is the thing that does the job, and you can actually obtain that by considering the minimization problem, applying Lagrange, method of Lagrange multipliers. And we did that in the notes. So I did the problem 328. Okay, and from there it'll fall with enough calculation. As in 334, which they tell you just do it. Okay? Find SSH in problem 334, which means plug in this beta tilde. Okay? And then this SSH, this formula for SSH is recorded in the book. Okay? However, you don't really need to do it if the constraint is something that I can incorporate in terms of my model. Let's do it. Do a real quick example. I have 2 minutes. Okay. Suppose I consider the following data, which is shown in the notes and the printed out pages. Okay? I made some fictitious data where I've got y is equal to beta 0. My model is y equals beta 0 plus beta 1 x I goes plus error. I goes from 1 to 14. It's one linear relationship. I goes from 1 to 14. It's a different linear relationship. I goes from 15 to 25. Gamma 0 plus gamma 1 xi plus epsilon I. Potentially different. I goes from 15 to 25. So there's 4 parameters in the model. What does the X matrix look like? I've shown it on this first page, number 11 of the notes. It just looks like a column of ones and then zeros in the first column, corresponding to beta 0 is included. Okay, but then after the first 14 observations, beta 0 was not included. That's the zeros. Instead, a different parameter is included, namely gamma 0, which corresponds to the ones in the third column below I equals 14. So then you have the beta 0 column, the beta 1 column, the gamma 0 column, and the gamma 1 column. Okay? Did you get a shot of that? Okay. That's the X matrix. So it's 4 columns. So the full model has 4 parameters. That's how I model this problem. There's no intercept because there's no column of all ones. Even though there's 2 intercepts, there's no intercept per se in the X matrix. Okay, because of the way it's done. It's easy to calculate X prime X. It's just block diagonal 2 by 2 matrices. So its inverse is actually would not be difficult to compute by hand. Though I did all this stuff with the Excel. Okay? And we can go over this again a little bit next time since we're almost running out of time. But what I do is I'm going to consider a certain hypothesis. Namely, the linear hypothesis I'm going to consider is that beta 1 equals gamma 1 is equal to 3. That's the null hypothesis I'm going to consider. That's a general linear hypothesis. It's of the form T beta equal to C. What's T? T is equal to, I'm going to write this as beta 1 equals to 3. There's 2 equations. And gamma 1 is equal to 3. Well, beta 1 is the second regression parameter, so that's 0, 1, 0, 0. Gamma 1 is the fourth parameter, 0, 0, 0, 1. So I get equal, this is T, beta, which is beta 0, beta 1, gamma 0, gamma 1 is equal to 3, 3. So my C is 3, 3. And my T is this. So that's how it would be in terms of the T's and the C's. Okay? So my SSH would be like this. Okay? And I can plug everything in. Once I got my beta hat. This is the full beta hat. Full model. Full model beta hat. Okay? What would I get? How would I do it if I was going to do it by hand and hang at this formula? Okay? Well, what I'm doing is I'm kind of illustrating this beautiful formula. Okay? The formula is, how would I do it without the formula? Here's how I would do it. I'd say yi, if the null hypothesis holds, what is the reduced model? The reduced model is yi equals gamma 0 plus 3x, beta 0 plus 3xi plus error. I goes from 1 to 14. And yi equals gamma 0 plus 3xi plus error. I goes from 15 to 25. So what I'm saying is that the slopes of the 2 models would be the same. Okay, they'd go up at the same slope, but there's a discontinuity potentially. Okay, and both slopes would equal 3. Not only are the slopes the same, but they're both equal 3. Okay? So that's kind of a strong hypothesis, so let's just play with it anyway. Okay? Because I made the data up to kind of fit that situation. I just threw some data in there. Okay? How would you deal with that? How would you analyze this model? What is this? Is this... Okay, how would I analyze this? How would I find the... minimize the squared error in estimating beta 0 and gamma 0? The way you would do it, you would simply take all this 3xi and put it on the other side and call it zi. So I'll call zi equal to yi minus 3xi. And I'll write this as zi equals to beta 0 plus epsilon I. I goes from 1 to 14. And I'll call it gamma 0 plus epsilon I goes from 1 to 14. So relative to these pairs of data, this model is equivalent to, I just have two different intercepts. Okay, and no slopes. So, because now I just have raw data here, 3xi, there's no parameter in there, right? The parameter is gone. And if I just go ahead and make a column zi equals y minus 3xi. That was on the previous page, right? Did you notice that column ahead here?
Yeah.
Z equals y minus 3x. Why did I do that? So I could do the reduced model by an analysis of variance table. I still have to take the reduced model. I still have to take the two intercepts. So I have a W matrix, the ones and zeros, and the zeros and ones, and the W matrix there. So that's my W matrix for the reduced model. Again, no intercept. So when I calculate the analysis of variance tables with Excel, I use the no intercept. But I use these two columns as the regressors for the reduced model. I use two regressors for the reduced model, four regressors for the full model, and check the box no intercept, or constant is 0. Okay? And I get the analysis of variance, and I simply get the difference of the SSH by both calculations. I calculated both by this formula or by SS res reduced model minus SS res full model, and I get that this is equal to 31.829 minus 29.645 equals 2.184. And I also get it by this fancy dancy formula over here. It's 2.184. Just wanted to check it. And of course the F ratio would be F naught. It turns out the way I cooked this data up over sigma hat squared full, there were 21 degrees of freedom, less for error. Okay? So sigma hat squared full, which came out to be 1.48. So this is something like a 1 over a 1.4 or something like that. And so it was less than 1. So I certainly failed to reject the null hypothesis. The null hypothesis seemed to be actually true. Failed to reject H naught. This actually was a pretty decent model for what was going on. That's the general linear stuff. Sorry I had to rush so fast at the end. We can go over this a little bit next time, just if you want to look over this example again.
Would that be considered?
This would be considered, we are done now.
Just the general linear stuff.
Through 3.3.
Through 3.3.
And 3.4.1, which I did confidence interval for the mean response. I don't think I'm going to do simultaneous confidence intervals, so we're done through 3.4. Prediction, I said in passing, so we're done with 3.5. Hidden extrapolation we have not done, so we'll do hidden extrapolation 3.6, 3.7, 3.8 next time. Okay? We're down through 3.5.